A couple of weeks ago, I've built a new iOS app, a web backend, and a Swift package. All of those things are actually part of a single telemetry service that collects usage data for my app checker. It's basically like a Google Analytics alternative, but tailored specifically to my needs. I've never built something like this end-to-end from scratch, so it seemed like an interesting, fun side project. And besides, I had this server in DigitalOcean doing basically nothing, just serving a bunch of static files. So if I could run my telemetry service there as well, I would get it for free, which would be a nice bonus, wouldn't it? So what are we doing today? I'm going to show how to build a service like this from the ground up, designing a database, building a backend that receives the events, building Swift SDK that sends the events from user's device, and finally putting together an iOS app that fetches all the collected data and shows a couple of nice charts. Just in case the full code is on GitHub, I'm not going to focus on every single line, so make sure to check links in the description if you're missing some details. Regarding the tech stack, for iOS dashboard app and client SDK, it's simple, just Swift, Swift UI, and Swift charts. For the backend, initially I thought to experiment and build it in Swift as well, but I wanted it to be done relatively quickly, so I went for TypeScript and Node.js, which I know quite well. And the database will be just SQLite. I understand SQLite for a telemetry service might sound crazy, but hear me out, I'm not building a public service, right? This thing is for a single app. Considering that it now has about 500 daily active users, it will generate 3,000-4,000 records per day, which is practically nothing. And even when database will have a few million records in a couple of years, SQLite can handle this without any issues. And in return for choosing SQLite, I get a database with practically zero maintenance, which is a huge upside, of course. For the actual database schema, I know that events that I'm going to send from the app will all have the same basic structure: event type, unique device ID, event date, and a list of parameters with their values. Parameters, of course, will be different for every event type. So the schema I ended up with is just two tables, one for events and one for event parameters, where every parameter would have a reference to the event it came from. Super simple and flexible. We'll look at the database again once the data will start coming in. Okay, time for the backend hello world. As I mentioned, I'm going to use Node.js. Not proud of it, but it does the job and I know it quite well. Let's disable Copilot for now because it will suck all the joy out of the process. Once the project has general structure and becomes less creative, I'll reconsider. Starting with the general scaffolds to create a server, attaching it to the port, and handling necessary stuff like a graceful exit. Then in the request handler, I'm taking the HTTP method and the path name to see if I have a handler function for this kind of request. For now, the only handler will be getHello, and it will just respond with a hello world. Classic stuff. And seems like everything works as expected. Beautiful. Next, I'll need an endpoint which will receive incoming events and save them into the database, which I don't have yet, so it's a good time to set it up. To work with SQLite from Node.js, I'm going to use a better SQLite 3 package because native SQLite support in Node is still a bit shaky and limited, but this package will be the only third-party dependency. I'm creating a function that takes a path to the database file from the environment, creates and returns a new database connection. Then I just store that connection as a top-level constant that I'm later going to pass into individual request handlers. And the last thing regarding database setup is to actually create the tables with the schema I described before. Now when I start the app, I should see the empty tables created. Nice. In just events, request handler will accept an array of events, not an individual event. I'll explain why this part is important when I'll be implementing the client which sends the events. Here I'm just first parsing the request body and making sure it's in the expected format, then preparing two insert statements, one for event and one for a single event parameter. Next I go through the received events, and for each of them I'm also going through its parameters and running the prepared statements to insert data into the database. Important thing here is to do this in a transaction because even though I'm writing data data into multiple tables, each event and its parameters are still one logical entity. And if, for example, insert operation into the events table fails, I don't want to leave a bunch of loose records in the events parameters table, so it ensures data integrity. And besides that, SQLite will batch all write operations inside the transaction, so there is a performance benefit as well. Now I'll just add this new handler to my routing function and then make a request with some test data to make sure everything ends up in the right places. I'm also going to need some authorization mechanism because this thing will be public on the internet, right? So the idea is to grant access to those requests that provide a valid authorization token in the header. One ingest token will be used by the client that sends events from user devices, and another read token will be used by the app on my phone to get the data and show the charts. You might ask why 2 tokens instead of just 1? That's because there is no way to protect the token that is stored on user's device. It will be inside the app's binary, which can be disassembled, making it basically a public information. It's not even so much an authorization token, but rather just an identifier. And this is a common flaw of all analytics services that send data from users' devices. The read token, on the other hand, is an actual secret, so anyone can write to this API, but only I can see what's inside the database. The code here reads those 2 tokens from the environment when the app starts, and then for every incoming request, it checks whether the token provided in the authorization header has access to the endpoint it's trying to reach. Testing this again from the terminal, a request without a token will get an unauthorized response, and with a valid token, it comes through normally. I've thrown together a simple test application that sends an event to the backend every time one of the circles is tapped. The event name is circle tapped, and it has the color as the parameter. And this is a very naive implementation of a telemetry client. It spams the backend with requests, it drains the user's battery, again because of all of that network activity, and it's useless when the device is offline. All events will be just lost. So now I'm going to build a proper client to address all of those issues. The general idea is to, instead of sending a request immediately after the user does something within the app, the telemetry client would first put all of the events into an internal queue, and only once in a few seconds it will check if there is something in that queue, then take the next batch of the events and send them all at once with a single request. This is why I've implemented the ingest events endpoint to accept a list of events instead of single ones. And if it tries to send the events, but at that moment there is no internet connection or the telemetry backend is not responding for some reason, it will just put those events back into the queue and will try send them again later, so nothing is lost. Something like this would already be way better, though there is still a major missing part here that will lead to lots of missing events. I'll first implement the events queue and then explain what this major problem is. It's quite subtle and I didn't handle it the first time I was implementing this client. I'm creating an actor called telemetry client, and I'll explain why it needs to be an actor instead of just a class in a moment. The client will take the server host and the ingest token for authorization from outside, and it's going to store the queue of events ready to be sent as an array. And this events queue variable is the reason why the whole thing needs to be an actor. It's a mutable piece of memory that can be accessed and modified from different threads. An actor will make sure that no 2 threads are accessing this array at the same time, creating a data race and potentially leading to some inconsistent state. Then I'm adding a method that adds a single event into the queue and another method that takes a chunk of the queue which needs to be sent. The method that actually sends the events is just normal Swift network call plus a bunch of error handling and putting the events back into the queue in case it fails to send them for any reason. Now for convenience, I'm also adding one shared instance of this client as a static property that can be accessed from any part of the app, and then another convenience method to send a specific event. In this case is the circle tap event. In my production implementation of this, I've extracted all of those convenience methods into another class, but it's just a pure organizational improvement. So now I can put events into the queue, but I'm still missing the part where the client sends them over every few seconds. For this, I'm using a provider pattern that I often use in my app, and it's super convenient for this kind of global things that should be initialized before the rest of the app. Practically speaking, it's just a normal view modifier, and in this case, it's going to hold a timer timer that is triggered every 5 seconds, and when it's triggered, I'm calling the send function of the shared telemetry client instance. Important in here is to wrap the sending part with the background task, so the client has enough time to finish the work when the user leaves the app, but the client is still sending something. Okay, so now to the final issue with this client that I mentioned earlier, and it's actually related to the app going into the background. Imagine user does a bunch of stuff in the app, we put all of those events into our queue, and then user closes the app and it goes into background before the timer was triggered. Which is fine, events are still in the app's memory, and when the user opens the app next time, we will have a chance to send everything, right? But there is also a high chance that either system will kill the app while it's in the background because it's low on resources, for example, or the user goes to the app switcher and kills it manually. In that case, of course, all events in the queue will be lost, which is not ideal. To solve this problem, every time the app goes into background, I'm going to serialize all the events in the queue and put them into a file. And every time the app becomes active again, I'll check if there is something in the file and restore the queue. The save function encodes the queue into JSON and saves it into a cache file, and the load function just does everything in reverse. Then in the provider, I get the current scene phase from the environment and call either load or save function depending on the current phase. Okay, now as I have some data in the database, I'm going to create two endpoints in the backend service. One endpoint will return a time series data, which I'm going to use to create a bar chart that displays the number of times each circle was tapped, grouped by, let's say, 1 minute intervals. And the second endpoint will return the total number of how many times each circle was tapped, and I'm going to use the data to draw a nice pie chart. For the time series endpoint, I'm selecting events, then joining them with event parameters using the event ID, filtering only the circle tapped events, grouping everything by the unique combination of timestamp and color, and then counting how many records ended up in each group. And for the pie chart endpoint, it's the same query, only this time I'm ignoring the timestamp and only grouping by the color parameter. Once again, testing the new endpoints from the terminal, and now I'm switching back to Xcode to create a new app that will transform this data into charts. New project, adding structs for the data returned by the backend, then a bit of a boilerplate code for making the network request. I want to fetch data once the view appears, and also I'm adding pull to refresh, saving the fetch data into state variables, and now it's ready to be displayed on the charts. First one is a bar chart with timestamps on x-axis and the total value on y. I'm also adding a mapping so that the red, green, and blue are actually red, green, and blue on the chart as well. The pie chart is basically the same, only using the sector mark instead of the bar mark and the different state variable, and here you go. The real app I've built for myself has a few additional bells and whistles, more screens, better code organization, but data structures are identical and overall is the same idea, fetching stuff from the backend and passing it over to various Swift charts. The real backend is also a bit more complex in the sense that SQL queries are more sophisticated, there are more endpoints and it returns additional metadata, but again, the overall design is exactly as I described in this video. It serves on average around 4,000 requests per day, that means one request in 20 seconds, which is practically nothing. Even my cheapest instance in DigitalOcean didn't even notice that something was added. I'm still utilizing less than 1% of its CPU capacity. From a pragmatic standpoint, it makes zero sense to build a thing like this, I know. However, it's super fun, I learned a ton of stuff, built something useful for myself, and overall I feel I came out of it as a better developer. So again, links to the source of the whole thing are in the description, but that's it for this one. Thank you for watching. Cheers.